Thank you. Thank you for inviting me to this workshop. And we will switch gears now compared to what we had in the morning. And everything fine? Yeah, and talk about something that I think we all as citizens are one way or another concerned about, and that is, of course, climate change, or in general, environmental issues and problems and challenges that we are facing. But I don't know, all of you, maybe some of you are working in fields close to that, or maybe you are working in those fields, but maybe not. And therefore, the idea was also that I will also talk a little bit about, in general, what this field, and of course, it's not possible to overview the entire field, but at least to give you some kind of very, very sketchy overview of what kind of models are being developed in that field, and yeah, how one can use, for example, techniques of optimal control to solve those models. And really what is key in the title of my talk is the second part, and that is about the stories, because I'm very much convinced that changes in the society can happen through stories. So they don't happen through a kind of neutral and yeah, factual knowledge. So that is only a little part, and rather we are all driven by stories. And historically, we also can I think confirm it in many cases that societies changed because there were compelling stories that drove those changes. So what I would like you to see from my talk is how these formal models, and of course we can only overview a handful of them, and I'll try to present to you 3 examples, but of course there are hundreds and thousands of such models, but how they can inform the stories and what kind of stories they inform. And also that we perhaps become more aware of, next time when we are discussing topics like this, even not as scientists, as citizens, we know that the stories we are told, they often come from models of different kind, for example, from models like that. And so we have to, as scientists, of course, think of those stories and models and how they interact. But as citizens also, we have to be aware that where those stories come from. Yeah? So I will try to discuss that a bit. And does this work? Did this work? Did it work before? It would be really good. Oh, no, maybe I can switch it on now. Yeah. Did this work now? Yes. Okay, great. Yeah, so that's what I want to try to achieve in this talk. So optimal control theory. So many of you obviously have background in machine learning, maybe in control theory, but optimal control theory is yet another branch and very often uses a bit different language. So I'll try to very briefly overview that and remind ourselves about some key facts there. Then we will jump to, again, some very basic facts about economics of climate change so that we could then discuss those examples that I was talking about. And then, of course, as I said, so key will be to, I hope you could see the connection between model assumptions and those stories and why we build certain models and what we try to achieve with those models. Yeah, so very briefly, again, there will be some mentions of some theoretical facts and useful, let's say, tricks from optimal control theory. Not so much, but some. And in particular, one example how one could, rather simple model, derive an analytical solution, and again, how this analytical solution actually helps us to tell a richer story, perhaps. Yeah, and so of course there will be a lot of information and also these 3 examples that I will try to discuss very briefly. So no need to follow every detail in those models. It's clearly not possible in such a short talk, but if you could get some kind of key points, so that would be great. And if you're interested, of course, you can then read about those models in greater detail. So first, let me put here some basics from optimal control theory, specifically in application to economic problems. So there are different, again, formalisms, of course, in optimal control theory as in any theory, but when it's applied to economics, very often we talk about problems of this kind, like here on the right-hand side. So you typically would have an integral as an objective function, the integral over time period. So the upper limit can be finite or infinite. Very often in economic problems, they actually think of an so-called infinitely living agent that decides on something. So of course, none of us is an infinitely living agent, but the assumption is that even Elon Musk is not infinitely living agent. But the assumption is that it kind of doesn't matter, and sort of the whole humanity as a whole is a infinitely living agent, so to say. So that's an abstraction that economists have agreed to use in this context. And then, of course, there is always a dynamic system, which typically looks like that. And often it has an initial condition, but does not have a terminal condition. But there can be also other models with different conditions here. So, and we have state variables, a state variable x, which of course can be a vector, and the control variable u. Very standard notations here. And yeah, this would be like a typical problem. So we want to find such u so that this objective function is minimized. So what is important to recognize is that these controls are chosen from a certain class of, from a certain functional class of functions, right? And also such that this function satisfies so-called geometric constraints on control. So often there is a confusion here. So it's really important that these both constraints are very clear. So the geometric control means that at every moment of time, or almost every moment of time, controls are within, let's say, certain bounds usually, and the functional class means that we have to define what kind of function our control is. So what kind of functions there can be. The typical ones are piecewise continuous functions, so those that are continuous everywhere except for a finite number of points. So there can be some breaks of discontinuity, but only the finite number. Or it can be a measurable function. So it can be many, many different points in which the function is discontinuous. That is important because for different applications, some of those classes may be preferred than others, or the other way around. So some classes may not be preferred than others. Yeah? And therefore, the optimal control may change depending on this class. So this is an example, a very classical old example called Fuller problem, which looks very, very simple. So you can see it here. So the dynamical equation is a typical Newtonian law. So we want to steer a mechanical object, a point particle. U is the acceleration. So the particle, the initial condition is here. So the particle is located here in x0. And we want it to move from x0 to, for example, 0. It can be anything. But also, there is an initial condition on the velocity. Yeah, so, and what we want to achieve, so this is our objective function. What we want to achieve, we want this particle to move to 0 as soon as possible and stay there. So the arrow must be as small as possible. Yeah, so this is the arrow term. What can be simpler than this problem? Very simple, yeah? So I will not ask you and test your intuition what the optimal control actually should be. I will tell you the answer right away, because the answer is not trivial. So the answer is that it's optimal, contrary to what one may think, that we just move here and stop. It's optimal to control this point in the following way. So first, the object should move as fast as possible to the left, pass 0, go somewhere further to the left, then stop here, turn around, and go back, and like a pendulum, oscillating pendulum that only eventually converges to 0 like this. Yeah? So this is what the solution to this problem is. Of course, if one gives it a second thought, one can say, yeah, this is maybe obvious. But maybe it wasn't so obvious until one hears the answer. So what it tells us, and that is exactly the example of what I was talking about just a minute ago, that the optimal control can be a measurable function. So it may not be that more convenient function, for example, a continuous function or piecewise continuous function. So even in very simple problems like this, it can actually be a measurable function. And what do we learn from that is that if we wanted to solve this problem by discretizing it, we probably would not realize that the optimal control is like that. We would just miss this chattering behavior at the end of the interval. So we would just see some jumps between 0 and 1. So this, by the way, so-called bang-bang control, and between -1 and 1, I'm sorry. We would not realize that this is really the real optimal control. So even in such simple example, of course, here, maybe we could even still guess it, maybe not. But in more complex problems, this would not be probably possible. So that is the value of optimal control problems, so that they can consider the system in the continuous time. And sometimes through techniques, not always, but through some techniques, in some cases, one can really see this kind of qualitative behavior very clearly from those models. Probably more clearly than one would have seen it from similar problems in discrete times. So how to solve those problems? There are two major theories. Of course, there is much, much more, but like really, really foundational elements of the theories are two. Is so-called maximum principle that provides necessary conditions for optimality, and another approach, which you are probably more familiar with, dynamic programming, which reduces the optimal control problem to a Hamilton-Jacobi-Bellman equation. So you must be familiar with that from reinforcement learning. And of course, numerical methods. So since some time, it's possible to discretize the problems really on a very finite grids, and of course convert them to simply numerical optimization. That is very straightforward way, and of course this way works in many cases. Or one can still use some of those theories, such as, for example, again, the first one, the maximum principle, that allows us to write down the necessary conditions for optimality, which is a set of differential equations with boundary conditions. And then by solving those differential equations, so we can basically solve under some additional assumptions, solve the optimal control problem. So it's easier to solve differential equations than the original optimal control problem, of course. So jumping now to the application area, which we will discuss today. So we discuss economics of climate change, and as I already mentioned, and plots like this, I think by now everybody knows. So we observe how the temperature is increasing, also historically over here, and how it is projected to increase over years here with the more and more accumulated greenhouse gas emissions in the atmosphere. So this is the major challenge, of course. When we talk about greenhouse gas emissions, we talk about both so-called industrial emissions and agricultural emissions. So it's the total, as it's called, anthropogenic emissions that we are talking about. And despite all the efforts of the international community, all the scientific efforts and so on, of course, as we all know, these emissions continue to rise. And that really represents a challenge, because climate change, of course, produces many negative impacts, yeah, from sea level rise to heat waves, to droughts, to floods, and you name it. So how do we connect these two topics? So optimal control, economics of climate change. The reason why we connect them, and they connect naturally, is because what we observe here is so-called intertemporal trade-offs. Yeah? So the problem of climate change is that involves very long time horizons. So that's due to, obviously, inertia of the Earth system, but also inertia of our economic system that cannot change overnight and suddenly switch, for example, to a different technology. It's not possible for so many reasons. So therefore, this time dimension is really critical in the economics of climate change, and optimal control exactly deals with time or time-dependent processes. Yeah? So that's why it's quite natural that optimal control was used already in the very early phases of the development of economic of climate change. So the other notion that, again, is very important to understand when we discuss these topics is so-called social discount rate. So what is really here playing a big role, and as we will also see in my examples, is how we see the future, how we value the future compared to today. So all models, or most models, that serve to support decisions in the context of climate change, they introduce so-called social discount rate, and that is how much less the future is important compared to today. So if I today can have $100, what the same $100 would mean for me in 1 year from now, for example. Yeah, so what would you prefer? Would you prefer $100 now, or would you prefer $100 to have it in 1 year? All of us, or at least rational choice, would be to prefer it now, because who knows what happens in 1 year. Yeah? And so how much we actually discount, is called discount, how much we discount the same amount of, whether it's money, but yeah, let's focus on money for simplicity. So how much we discount the same amount of money in the future compared to today is called social discount rate. And there is a big debate in science how much it actually should be. Do we discount it at 3% rate or at 5% rate, or it should be 0% rate, and we should not discount the future. So that, of course, or even have a negative discount. So that all of that discussion is taking place. But traditionally, there is some values between maybe 3 and 5% that are typically used in those models. And everything I have said so far about climate change had to do with the global level, as if we consider the system as the whole system. And that is, of course, because climate is a global phenomenon. Greenhouse gases are mixing in the atmosphere, and therefore it's a very global issue. What happened? But decisions, yeah, thank you. But decisions, of course, are taken by countries, and even some decisions are taken by countries, but some decisions are taken by people or by firms or by very different kind of decision-making entities. We will not be discussing that aspect, so it's in itself a very, very complicated issue, how countries should cooperate or how they cooperate already or don't, and all these issues related to so-called free riding and so on. So this is not, it's very important for climate change, but this is not the topic for today. So today, let's focus on the global picture, and then let's see what kind of stories we can tell with optimal control at the global level. Yeah, so how do we, how do we model this, or how one would typically model problems of the economics of climate change? Again, it's very simplistic. There are many models that are much, much more complicated than this, but this is just some basics. So typically, for the optimal control setting, we would introduce an objective function like this, where this term here, exponent, is exactly the social discount rate that we just discussed. These are examples how the exponential discount rate is working. I guess all of you can easily picture it yourself. We don't need to discuss it so much. Then what we have here is u, so not to be confused with the control variable from the previous slide. So that's a different u. So here, u is the utility of consumption. That's a very important notion also in economics, which tells us that utility, so how a particular amount of consumption is useful for me, is not a linear function. So if I can consume, again, $100, and then I compare it to consuming $200, so the usefulness of that is not twice as big. It's less than that. So every next unit of consumption is actually less valuable compared to the previous one. It's still valuable, so it's not meaningless to increase consumption. But typically, we assume that the usefulness of, would call it usefulness, but the economic term is utility. Let's say this, or maybe this yellow curve is more realistic, or the pink one is quite extreme. So it would look like this, right? So when we have very low consumption, so there is a lot of incentive to increase it. And I think we all can relate to it from our own life. So of course, when we have low income, any possibility to increase it is obviously very welcome. When we reach a certain level, it's still useful. It's still good to further increase our income or consumption, but somehow it's less attractive. Yeah, every next unit of consumption is less attractive than it used to be before. So this is expressed in this u function, which is typically a concave function of consumption. C small is a consumption expressed in monetary terms. Yeah. And then this model operates also with another very important notion that one should really be aware of in those discussions, and that is so-called representative agent. So what economists typically assume is that there is a so-called representative agent that represents somehow all of us. Yeah? So we all are different. All of us would have different, for example, social discount rate. We would have different function, utility function, of course. This is recognized. However, there is some kind of average. Yeah? So one can think of some sort of average consumer. And in order to make those models at all solvable and tractable, economists again have come to that convention to use so-called representative agent that, yeah, is some kind of average consumer in the society. So in this more, let's say, very, very classical formulations, we talk about this representative agent and the consumption here of representative agent, but then we multiply it by the population size. So to account for the entire population, so to say. So this is obviously an approximation, but approximation that actually works, obviously with some degree of accuracy. It's not perfect, but it already can give us some very useful insights. And then really the key notion of the economics of climate change is rather simple and again intuitive, although it's expressed in quite complicated formulas of models, but really the foundational notion is very, very simple. And that is that when we want to think of a rational decision, how we deal with climate change, yeah, really rational in economic sense, not to say that that's the only way to deal with that, it's just one way to deal with that. But in that case, we would think of it as a cost-benefit analysis, taking the benefit of some action X here, some abstract action, and the cost of, again, some action X. And then, of course, if we want to maximize a function like this, under some reasonable assumptions, we would come to that very simple equation that the marginal costs and benefits must equalize. So whenever we see very complex economic model that analyzes trade-offs of different actions, so somehow at the bottom of it is always this notion of costs and benefits and marginal cost being equal to marginal benefit in the optimal point. I come now to a very classical example of in this field of the economics of climate change, which is the DICE model. And I'm sure many of you heard about it, if not before, but when the author of this model, Bert Nordhaus, got the Nobel Prize a few years ago. So it was quite, I think, a lot of information in media, and you surely heard about it. It was one of the first, or maybe even the first model of this kind, and then many, many other models have been developed by different authors who were inspired by this kind of research. So the key idea of the model is here. So it has 6 dynamical equations, so of the kind that we saw before in a abstract formulation that I had on the previous slide. So now these are concrete equations that describe one equation for economics. So it describes how the economic output is generated, and then some equations for emissions, concentrations, temperature. And then this is the key element that increased temperatures lead to so-called climate damages. So climate damages is some kind of factor that negatively affects the economic output. So the higher is the temperature, the more are so-called climate damages. Again, where they come from floods, from droughts, from heat waves, from many, many other negative impacts of climate change, but they all are aggregated, again, in the economic terms, so to say. And the assumption is that economic output is decreased because of these climate damages. So the dynamics in the economy is happening because of the capital stock, which accumulates when we invest, and that is done through so-called saving rate. So we are investing in the accumulation of capital, and then this leads to economic growth and growth of the output. Then there is this, as I showed on the previous slide, there is this utility of the representative agent, which we would like to optimize. And we come to that. But there is another, so saving rate is a control. This is what the representative agent decides, and have more saving rate or less. And how do they balance what are the trade-offs here. But there is another control, and that is abatement rate. So this is how much we actually invest in reducing greenhouse gas emissions. So again, as everybody knows, it cannot be done for free, so it requires investment. It requires investment in renewables, in carbon capture and storage, and so on and so on. So this is all captured by one variable that is called abatement rate. And therefore, we have two controls, saving rate and abatement rate, a system of 6 dynamical equations, and the utility, the social welfare function that we want to optimize. The solutions of the original DICE model, there are several versions, and Nordhaus is still working on it. Every 2-3 years, there is a new version that is released, and some parameters are being revised and improved, and so on. So it's a very, also, there is no specific notion of DICE model, but there is a series of models, and one should always be aware which version we are talking about, and so on. But generally, without going into those details, these are the kinds of results that one gets if one solves this model and finds those optimal controls and then optimal trajectories. So, and now we come to the story that this model tells us, and how influential it actually has been since its creation in the early 90s. And the story is captured probably mainly here, where we see that the optimal trajectory of greenhouse gas emissions, or CO2 emissions for simplicity, is going like this. So if we started somewhere in 2010, for example, this is the earlier version of the DICE model. So first it increases, and then it's actually optimal for the representative agent to reduce emissions, because of those damages. So if the world really worked like this, that there were one representative agent that could, in fact, first of all, of course, have all the full information about the system and all the knowledge and all the foresight and so on, and also would care about this infinite, or very long, at least, maybe not infinite, but very long time horizon, under some social discounting, but still, it would actually be optimal to, at some point, reduce emissions, and really emissions would go down, in this case, from the year 2055, and the problem of climate change would be solved. As opposed to the so-called baseline scenario, where there is no mitigation, and there, of course, emissions would continue to grow. So this is the emission picture, and here is the temperature. So here you could see that it's because of the time horizon, so it's 2010 here, and you can see that until 2010, so temperature would still grow, but here it would still decline. So if we could see the plot for a bit longer time horizon, we could also see not only the decline of emissions, but also the decline in temperatures, and temperatures decline later because of the inertia of the Earth system, but they would still decline at some point. So in some sense, and that has been a lot of critique to the DICE model for that this kind of rational approach and the cost-benefit analysis, at least when there is one agent responsible for the entire system, is sort of optimistic in a way. And do we really see that the real world is actually kind of following this model? Maybe yes, maybe no, or rather no, perhaps, but we are not yet in 2055. But at least until now, there are no signs of that we may expect such kind of solutions. And of course, on the one hand, this model has made really a huge impact on all of us, on the discourse in about energy systems, about environment, many systems, because it really highlighted these trade-offs and the fact that there are these costs and benefits, and if we balance them, what can happen. But on the other hand, perhaps the story is a bit too simplistic. So it has played a really big role to attract attention of people, also to introduce this kind of language and to introduce all these notions. And now we can actually discuss such kind of problems in this rational way. Yeah? So that's a big positive impact that I think at least this model has made. But then, of course, as any model, it also has limitations. And of course, for researchers, it means that we want to develop further models that can overcome those limitations. And I want to show you very quickly 3 examples of research in my institute that is called the IASA, which try to overcome these limitations, each one in very different way and very specific limitations, and address very specific concerns, as every model does. Yeah, and it's, as I was trying to explain or clarify in the beginning, that would be really good that we see how the assumptions of the model translate into the stories, and that and backwards. Like if we want to develop a certain story, how we should organize the model design, and how clear we should be about the connection between these two. So that is not always done exactly as transparently as maybe one would want. Anyhow, so in the first example, I want to show you how one technique from optimal control, which is called reachable sets, can actually be used and useful for models of the economics of climate change. So part of my picture disappeared. Okay. Yeah, all right. So in optimal control, as so far we have discussed, the main objective, of course, is to find that optimal control. And in, let's say, well-posed problems, there is a single optimal control that we find, and that is our solution. Yeah? But of course, it only tells us part of the story. So we have the entire model, we have the entire dynamics, and out of all of that, we only extract one point, one solution. So one, let's say, argument could be that we are actually missing a lot of information, and don't we want to know more about the model beyond just that optimal point? Because, for example, what if we don't reach that exact optimal point? So what happens then? So for that, this methodology of reachable sets, so we rather prefer to name them within reach sets, could be used. So if you could see let me try. So no, it doesn't show it like this. Okay, let me try to explain what was meant to be on this figure, because part of it somehow disappeared. So if we are here if we are, for example, find ourselves here in this point today, and for example, we want to locate ourselves, for simplicity, of course, at this two-dimensional space, where one dimension, for example, is economic dimension in general, whatever that means, and another one is environmental dimension, for example. And we are here. All possible trajectories that can start from the point where we are now form a so-called reachable set. So if you imagine all possible controls that one can apply there, which are obviously infinitely many, all of them, so they form some kind of set. So here, if you saw my full picture, you would see a rather big set like this. Yeah? And then let's think of it like this, that between today and some year X in the future, we apply a particular policy. For example, we apply a business as usual policy. So we don't have any extensive mitigation if we talk about climate change, and we just continue as we do now. Yeah? And then we find ourselves after some years X in this point. So most likely, yeah, the economic dimension increased. Actually, environmental dimension should have decreased. Let's assume that it's a negative X, is a negative axis here. And we are here now. And what is that space which we can still reach from that point? It's probably smaller. So in the figure that was here, so you would see a bigger space first, bigger space here, and then a smaller one here. So after applying a particular policy, we actually shrink the set of all possible states where we can, in fact, find ourselves in some more distant future. Yeah, it's a very intuitive concept, of course, but has not been used in the economics of climate change. So, because it kind of more comes from the optimal control theory, and somehow it hasn't really been, so to say, discovered by applied economists. So we thought that this might be a useful tool. And for example, here you could see examples how we apply that approach to the DICE model. This was already some time ago, so it's the old version of the DICE model. But here, for instance, so we start from the year 2000. Again, imagine how long this has taken. So, for example, if we start from the year 2000 and ask ourselves, what are all possible states which we can reach from the year 2000 in 2010? So between the year 2000 and the year 2010. This is this little space here. And the axes are, here is the economic dimension, which is capital, and here is the emissions, or actually accumulated emissions, concentrations in the atmosphere. Yeah, so this is where we can be. So we can have a lot of economic capital and a lot of emissions, or little, or all options in between. Of course, if we start from the year 2000, but then ask ourselves, what is the space in 2020? So then, of course, or what is it? Yeah, this is 10, this is 50, yeah, 2050. So now the area is already much bigger, of course, because there are, yeah, a longer time horizon, we can take different pathways, and of course it's bigger, and so on. So this is, for example, the state, or the all states that we can reach in 2010. So it sounds very intuitive, and one would say, okay, so what's special about it? The issue is that in order to construct the boundary of this set, one should really apply quite advanced techniques from optimal control. So it's not so easy to just, for example, have some kind of brute force search and have like many different, let's say, evenly distributed controls in some sense. So if you do that, most likely, and there are many examples that optimal control people produce to actually show it, that you most likely arrive only at the part of it. So in order to really have the full set, one should apply some theories, again, the necessary conditions for optimality that I showed before. So there is some technique that is required. But here this technique has been applied. And we can see how this set of all possible states is actually increasing. Okay, this already tells us something, so we can really see how uncertain is actually, or what, put it differently, so how the result of our actions is actually how broad it is. So we can choose that way and find ourselves here, where the emissions are really big, yeah, but also the economy is big. Okay, that's one choice. The other possibility is we could actually go here and have little emissions, but also little economy. Maybe it's good, maybe not. We could also aim at here and say, okay, maybe here not, but rather, let me see, here is the economics, yeah. So we may want to be here and say, okay, the economic capital is very high, good, but also emissions are low, perfect. So why do we not want to be here? Because the optimal control that leads us to this point is not the same that leads us to this point. And to trace all of that can be very interesting. While in, let's say, more traditional approach, what people do, they just find an optimal control. And where the optimal control is in dice model, it's here, in this point. So when we derive optimal control, normally, as most studies are doing, they only know this point. But what they don't know is the shape of the whole utility function. This is the utility function. And this entire space that is actually possible to reach within this model. So it gives us much, let's say, richer picture. And then, of course, how to use that picture for decision making, that's a separate topic. But at least this tells us the story about, yeah, all these different possibilities that exist. We can skip this one and go to another story. And this story, again, tries to address, again, a specific challenge. In this case, this issue of representative agent that many people would say, yes, but we are so different, so why all these models assume one representative agent? And of course, there are different ways how one can depart from that assumption and have different agents. So what we want to test here in this story is really the social incohesion, or the lack of social cohesion that we are observing in the society, in the sense that, again, you all surely heard about it many times, that the capital, the entire capital in the world, is concentrated, is hyper-concentrated in hands of very few people. Yeah? And there's a lot of discussion. I think recently there was yet another article that says that really the major part of emissions, greenhouse gas emissions, are actually produced by very few individuals, corporations, let's say a very small part of the society. Yet, when we discuss climate change, very often we hear stories that, yeah, people should change their consumption patterns and so on and so on. But if one looks at the profile of the emissions and actually sees where those emissions come from, they are very unevenly distributed in the world across different population groups. So here we were trying to relax just this one assumption of the dice model of the representative agent. Everything else stays the same. Just to see, what if we have two agents now? Not one, but two. Not 100, but just two. But these two are so-called capital owners. So those people who actually accumulate capital, and everybody else, which we called wage-dependent households. So it's all people whose consumption mainly depends on wages. They don't have their own capital. We don't have time, of course, to discuss the details, but basically what one can learn from a model like this are very interesting things. So we could really tell a story how the concentration of capital, either higher concentration or lower concentration, how it affects, on the one hand, so-called social planner problem, so in which we optimize the social welfare function that we discussed before. And on the other hand, how it affects the decisions that capital owners themselves take. Yeah, so there are two ways of looking at this problem. So on the one hand, we could say what is best for all of us. That is so-called social welfare function or social planner problem that we can solve here. So then it will look like this. So we would have consumption of capital owners and consumption of wage-dependent households, each weighted by their own population size. Or we could say, okay, so if capital owners actually own capital, then only they decide, because they own capital. They have economic agency. There are two ways of looking at this problem, and depending on the way how we look at it, we get very different results, such as, for example, that economic variables are not sensitive to this capital dispersion in the social planner problem. So from the social planner perspective, actually the optimal solution is not so different from the original DICE model. So one can argue so much that, oh, the DICE model is limited because it doesn't include that heterogeneity, but actually if we include it, the impact on the solution is very small. Not the result that one would necessarily intuitively expect. This is in the economic terms, but on the climate side, for example, this is not like that. And here we could actually see that the economic dispersion or the capital dispersion, which is described by this parameter Q, actually has the impact, and we can see that, depending on the different parameter, it can take different values. For example, so if we talk about social planner problem, then optimal abatement rate is higher with the higher capital concentration. So again, something that is paradoxical in the first glance. So the more concentrated is capital, something that we probably generally don't like. Yeah, but it actually leads to higher abatement rate from the social perspective. And that is, of course, because the weight of these capital owners in this function is small. And if the decisions we're really taking based on this, so if all of us had the same weight in the decision-making problem, then the capital owners would pay for climate change. And that would be better than the DICE model. We would solve the problem only if we could do that. And the model tells us the story. But of course, in reality, they have higher weight, right? And with a model like this, we could really show it now. So instead of just talking about it, we can really show it. There are many other stories here, but I'm looking at the clock and observing that I have to soon come to the completion. But before that, let me also show you another story here with the same model. And here, what we show is the difference between consumption in capital owner scenario, so when capital owners actually optimize for themselves, and no mitigation scenario. And that is also a very important story in the economics of climate change, because it tells us, and that explains or gives one reason, of course there are many other reasons, but it gives one reason why climate change is such a big problem. Why despite all these discussions, all the science behind it, why it is still so difficult to change it. And that tells us at least the partial answer, not the full answer, but the partial answer. And that is that even in this optimal scenario, which is optimal overall, optimal if we integrate over this entire time horizon of, usually time horizons, for example, in DICE model is something like 300 years. So if we optimize over 300 years with the social discounting, still the current generations have to pay. And that is, again, something on the one hand, everybody says, of course. But on the other hand, this other discussion, why we discount the future. So this concern that we discount the future and therefore we somehow don't take climate change so seriously. But even then, even when we discount the future. There's a really deep kind of paradox here. Even when we discount the future, we still expect the current generation to pay. So this whole criticism that because we discount the future, it's all not sort of fair and correct, maybe not so simple again as it sounds, yeah. And that is, of course, no one wants to pay for that, and that's why we are where we are. And again, this model really showing it in a way that allows us to discuss it and allows us to also analyze it. For example, we can ask ourselves how to decrease that, let's say, call it sacrifice, yeah. Again, it's not here on the slide, but in this paper that we are working on, so we are trying to actually find a way to decrease this period and therefore to find plausible, let's say, policies that can avoid or at least reduce that kind of sacrifice, again, let's call it, that is required. So these models, again, allow us to explore stories of this kind. The third example I will present very, very quickly, and the main point of this example will be that sometimes it's even possible to solve some models analytically or almost analytically, and that gives us also really a good basis for stories. So this particular model, again, the details actually can be read here, so I don't need to really discuss it so much, but again, so a framework that is quite interesting, I think, and useful. That has been developed in the economics of climate change is to distinguish between two sectors. So rather than having the whole complexity of the real economy, which of course there are so many things that one should look at there, one could really abstract from it and analyze really the foundational issue. And that is in a very, let's say, simplified form that we can talk about so-called green sectors and brown sectors. So in a very simplified way, our task is, or the task of a decision maker that worries about environmental change is to transit from the brown to green economy. Yeah, so it's a very, let's say, caricatured way. That is really the essence of the problem. And so it's a very simple model. What one can show, really analytically, let me jump over that, is that even when we have, yeah, that is important. So even when we have, oh, let me say it like this first. Of course, the reason why we cannot easily transform our society from brown to green economy is that the green capital or green sector is not as productive as the brown sector. If the green sector were, let's say, better economically than the brown sector, then there would be no issue and we would already have the green economy already a long time ago. Obviously, this doesn't happen. Why? Because still, with fossil fuels, we can produce cheaper goods and services. That's very simple. It may change in future, but at the moment it is like this. So in this model, we really show that this productivity difference really makes this task, of course, of this transition very difficult and requires what we can be interpreted as a political will. So we must actually have some additional incentive to prioritize the green capital. And let's say that we have that incentive by adding this kind of term in the objective function. Yeah? So we have the economic side, but additionally, we have a political will. We just say we want to have this green sector. Regardless of the economics, we want to have it. And the interesting result here is that this is not enough because of that difference. And again, we don't have, of course, time to discuss it really in detail, but the interesting thing here is that one can really show it from the optimal control model and the solution that we get, that if our dynamical system, our economy, starts at the point where we have a lot of brown capital, so this is capital B, and not so much green capital, so somewhere here, then the optimal solution is such that we have to go as fast as possible to this line. And this line is a ratio, a certain ratio, a given ratio Q, which is dependent on some parameters, doesn't matter. So we have to go from this point to this line as quickly as possible. And then the optimal trajectory is going along this line, which means that in the optimal scenario, we must have both capitals. We cannot eliminate brown capital, and it must stay in order to sustain the economy, as long as this productivity difference exists in favor of brown capital. And that is also a story. That may be a sad story, but a story. And again, the question is how to overcome that. And another model or a more sophisticated model is needed, of course, to show it. But I'll stop here. Yeah, and this is the main insights or main topics that we have covered. Just to recap, optimal control relies on the description of dynamical systems using differential equations and continuous time. That was the main thing. There are theoretical models, and they can be sometimes solved, sometimes analytically, but in most cases, of course, not. And what is called stylized models, so the models of the type I was showing, can actually inform stories, and they must focus on key processes. And of course, I meet every other detail that exists. And then we can see, let's say, the forest for the trees. Yeah, so really the essence of the problem and the story. Yeah, and when developing new models, it's essential to aim at the simplest model necessary to address the research question, but no simpler. That's of course a famous phrase. Thank you.
Maybe we'll go ahead. So thanks for a great story. I have a question. So you've been showing these refined models, focusing on these key aspects, and also focusing on the illustration of the outcomes, the solutions. To me, one of the key aspects that is left out up to so far is stochasticity. So, and then in particular, I would be interested in how would you tell the story or a solution that is stochastic or a control action that is stochastic and illustrate it, for instance, in this reachable set kind of ways. Do you have examples of that, or do you have ideas on that direction?
Yeah, it's a good question. I think there is a technical part of it and there is a conceptual part of it. Conceptual part is that what would be the source of stochasticity? For example, there are examples of models that say that this climate damages they are stochastic because, of course, yeah, droughts, floods, yeah, they can happen, obviously. Individual events obviously are stochastic. But does it really matter when we talk about the global scale and where like hundreds of those events happen every year and they probably more or less, yeah, average out? So that's a question. So I think the stochastic models, one should be, let's say, one should decide when they are really useful and when it's something fancy that, yeah, everyone would agree that of course many things are random in life, but that's maybe a little bit to my last point here. So sometimes we don't need to overcomplicate things, but of course, surely there are examples when stochastic models would be more useful. They are not so popular in this field, to my knowledge, I would say. Yeah, how to present the results is yet another big story. We are developing other models, not of the kind I showed here, but some others that have to do with the more kind of immediate decisions that decision makers should take, for example, on the land use, how to optimize the land use. And there we actually use a lot of stochastic modeling for those, and yeah, then showing some expected values, obviously, value at risk and all of that. So the standard approaches, yeah.
Thank you. I find the discussion about social discount very interesting, and I have two questions about that. First, is it mainly just based on kind of like an average view of how the average person will view that thing? And then they just say, okay, it's going to be a high number of 0.45 or whatever, and just
yeah, so they even surveyed some people and asked, yeah, how would you value, as I was kind of saying before, if you have $100 now, how much would you need to have in 1 year in order to feel it as the same kind of thing, yeah? And you say 110 or whatever, yeah.
Okay.
And then they derive some rate. But as I said, typical values are between 3 and 5%. That with every year it decays
And they base them really on that kind of specific experiment, or they also ask much longer term climate relevant questions to see what, like,
yeah, good question. Good question.
Would you rather have like a good house now, but your children won't have a house kind of question? Okay, interesting.
Yeah, yeah.
And a follow-up question about discount factors as well is, I guess you could also turn this around, right? You can ask like, given some other constraints on the cost we have and the resource we have, what social discount factor can we afford ourselves? Is that something that you have done, or people have looked at?
Not sure.
Because it could also help with the messaging, right? Like,
yeah.
Okay, no, I'm just curious if.
No, I think it's an interesting angle. So many people are doing so much research in this field. I'm hesitant to say it sounds very novel.
Yeah.
It sounds interesting to me, but it's possible that someone else has done it.
Yeah, I'm curious. I'll look into it. Thank you.
Thank you for your great talk. I have a couple of questions. I mean, the first is these models all seem to work on the assumption that there will not be like a widespread climate collapse that completely ruins the economy, right? That's a pretty real possibility that also needs to be taken into account, right? And that the social planners and the capitalists in these scenarios are probably not taking into account as really as they should, right? And my other question is, even for example, from the perspective of the capital owners, right? The calculation still looks at, say, like the 300 years from the collective perspective of the capital owners, right? Yeah. Is there research on, for example, how do the real capital owners that only live the next 60 years and maybe don't care about what happens to the next generations behave in this way? Or how that affects like the levels of abatement, like reinvestment?
Yeah, there is this different framework, but complementary to this, that is called overlapping generations models, OLG models, so-called. And indeed, they really assume like a particular lifespan for generations, and then there is another one, and so on. So it's actually there is a version of this model that was also realized in this OLG framework, and there, of course, one should always assume. I mean, if they only live, let's say, 60 years or 80 years and don't care about anything else, so then obviously, one can easily predict the solution. But in real life, we don't see that, right? So we see that people invest in future beyond their own lifespan. And capitalists possibly do it more than others. And therefore, from modeling perspective, what is often done is the assumption that because they are overlapping, there is some kind of bequest that they want to leave. And that's also part of their kind of motivation. And therefore, in a way, it actually becomes very similar to living forever. So there are some differences mathematically, but yeah. What was your first question?
The first question was more regarding, like if these possibilities, I mean, obviously the possibilities of climate collapse change the equation a lot, right? But I mean, obviously they would make action much more profitable, right? I would assume. But I wonder if these models have been explored, like how big is the difference, let's say?
Yeah, exactly. There are two ways how this has been explored, as far as I know, again, in a very simplified way. One was that indeed there were even more stylized models that I showed that indeed assumed like a true collapse. Often, at least some years ago, it was motivated by the breakdown of the thermohaline circulation in the Atlantic. So this kind of motivations. And indeed, obviously, in such models, you get very different results. Somehow, those models have not become, let's say, well, they are interesting examples of what can happen. But since we don't have really, let's say, statistics on such events, it's not an event that one can experience many times and have some certainty about it. Somehow, I think there is again, I'm looking for a better word than hesitance, but not finding it. Let me use it. So hesitation of community to really say, okay, let's put them in models like that. So one does it for curiosity, but not as a, let's say, as a serious projection of any kind. But then that's one line. And the second line was there were different damage functions that were tested. So Nordhaus assumed a specific functional form of the damage function, how the damage depends on temperatures. And some other researchers assumed some other ones, and of course more extreme. So there was, for example, this economist Weizmann that assumed quite extreme damage function, and then of course, yeah, results were recalculated. There, because again, from what I know, because of the social discounting, actually the difference between solutions was not as high as maybe one would expect. So there, actually, the social discount was really killing that effect. Because really high temperatures where this, so the way how they did it like this, that for lower temperatures, these two different damage functions were kind of similar. And then for higher temperatures, they really diverged. Yeah, so Weizmann one was much higher and Nordhaus was lower. And so to reach those high temperatures, we have to already get to, I don't know, closer to 2010 or something like 100 or something like that. And so there, because the social discount really mattered, and for values that were used, basically it killed any, I mean, there were some effects for sure, but not as big as one would maybe expect them otherwise.
Thank you very much.
Thank you very much. I want to follow up on this discussion because what you said about these collapse damages, the tipping elements perhaps, sounded very strange to me because of course we don't have statistics and data of these events, but that's exactly how we could utilize these models. And so maybe my question following upon this, is there a systematic or somewhat systematic way to analyze these models, taking into account uncertainty about the damages, either like forms of different linear damage functions or including abrupt damages, but with some uncertainty around and, you know, finding maybe some robust control over these uncertainties?
Yeah, again, what I know, and I surely don't know or everything that has been done in this field, is that papers I saw tested specific functions, let's say several different functions, and then they said, okay, if the damage function is like this, then the trajectory is like this, and so on, and perhaps some uncertainty ranges or intervals were included, but not in a systematic way in that sense. I think, again, it's my interpretation and it can be wrong. I think it's really the lack of this really empirical basis that somehow makes scientists perhaps a bit hesitant to invest too much effort into that. But that's purely my interpretation. I don't have the full insight here for sure. Basically, yeah, one could also, in the spirit of the previous comment, ask the other question or ask it another way around. So how much the damage should be to destroy the system, right? And because we don't have the statistics on the past, we can then say, okay, so that's actually our limit. But there's no way to verify it until we actually see it.